No.
No, well, we just moved backward.
And now that's
Yeah, that's it, working.
okay, good. So let's hope it continues like that. So the last topic of our course is transport in topological materials. And we will focus on one item, which is topological semimetals. Topological semimetals. So the plan is two parts. So today will be a brief summary of topological semimetals following the paper by Ari Turner and Ashwin Vishwanas, which is published on, probably is published in an ordinary journal, but its archive version is. So that will be a summary, a short summary of Weil semimetals, and that we'll do today. And next time, and maybe that will be the last lecture, we will study how the topological aspects of semimetals modify conventional Boltzmann equation and lead to a rather unusual anomalous Hall conductivity. Maybe it will take one lecture, maybe two, I have no idea. It's a rather new subject. So let's see how it goes. Okay, so what is Weil semimetal? So it's a 3D material. If you look at the 3D material, so it's a bulk of 3-dimensional material. You look in the K space, 3-dimensional material, and then you see that in the K space there are special points where spectrum is degenerate. Degenerate point of the spectrum. And typically you will have a number of these points. These points always come in pairs, as we will see, and we will always have an even number of these points. So as opposed to a story that is taught in a high school, when you have a valence band and conduction band, and they're separated by a gap, and we either have a metal if the chemical potential is in the conductance band, or an insulator if the chemical potential is in the gap. For Weil semimetal, we will have structure that very schematically will look like this. So there will be a point which is a touching point where if we sit on the neutrality point, the field valence band touches the empty conductance band. And there are many examples of this. So this type of materials, they're called semimetals, because they kind of in between metals and insulators. They don't have a finite gap between conductance and a valence band. So they are gapless on one hand. On the other hand, the density of states near the neutrality point vanishes, so it almost looks like a gap. Okay, and there are many materials that have this structure in various dimensions. For example, in 2 dimensions, a very famous material is graphene that has the same structure. But actually, if you look in many other materials, for example, gold, you will discover that deep down in the band, not necessarily close to the chemical potential, there are points where different bands touches, where there's a degeneracy point. And these degeneracy points will be very important for what I'm going to discuss today. So let us discuss the degeneracy of the spectrum. And let me contrast it with the spectrum that we discussed so far. So far, we discussed the spectrum within the effective mass approximation. So far, our spectrum was like this. So epsilon of k was k squared over 2m. So it was one important band. We focused on this one important band. We ignored all other bands, and therefore it was a single band story from the beginning of the course till today. And this is going to change. So now we're going to look at situation where we can no longer single out one important band. Instead of one important band, there'll be several important bands, and a paradigmatic example of these two touching bands. Okay, so that's why we talk about degeneracy. So what do we know about degeneracy? So let us think about some effective two-level model. So we have some effective Hamiltonian, which describes a two-level system. And two-level system, it can be a spin placed in the magnetic field. So imagine there's a spin placed in the magnetic field. Or it can be a double well. If you have a double well with two levels that have nearly equal energies, then hello. Yeah, thanks. And you. Fine. Okay, so we have two wells that are nearly degenerate, and if we take into account hybridization of this thing, then we'll see that this thing actually has two levels. One level will be corresponding to a symmetric configuration of wave function. Another will correspond to anti-symmetric configuration of the wave function intervals. But essentially, what is left over in the low energy description of the system, it's effective two-level system where we can ignore all the high energy states in this band and only focus on some reduced Hilbert space where two levels have approximately the same energy. So these are model system of two-level systems. Okay, can we dig in there? Let's see, because it's too strong. I hope. Okay, then what have we said? We said that essentially 2x2 level system, it's essentially matrix which is 2x2. And so it's 2x2 matrix. That in principle depend on some external parameters. Let's call these parameters lambda. And then we can change these parameters, this parameter lambda, and follow how energy level of this Hamiltonian changes as a function of lambda. And now it's a very simple model, but then you can compute the spectrum of this matrix. So let's do it. So it's 2x2 matrix. So we can always write a 2x2 matrix as a superposition of Pauli matrices. So let's call this combination of Pauli matrices F0 of lambda times sigma 0, which is an identity matrix, plus Fx of lambda times sigma x, plus Fy of lambda times sigma y, plus Fz of lambda times sigma z. Now, the first term just sets the onset of the energy, so it's just where this thing starts from. So let us set it to 0. It's not important for the equation of degeneracy. But everything else essentially tells us what is the splitting between energy levels. So the difference between energy levels, which is E2 minus E1, is what we get by solving this matrix equation, fx square of lambda plus fy square of lambda plus fz square of lambda. Okay, and now we come to the point of so-called symmetries. What most general matrices A, what are the most general matrices A are allowed? If symmetry does not constrain these matrices, if it's a generic 2x2 matrix, sorry, all these coefficients are finite, then to have a point of no degeneracy, you have to separately nullify each and every term here. So we need to claim that fx of lambda is equal to fy of lambda is equal to fz of lambda, and we demand that it's 0. So to have a situation when these energy levels exchange, and there is a point which is called a point of spectral degeneracy, or crossing of the levels, we need to kill 3 functions f. Now, if these functions follow from some microscopic parameters of Hamiltonian, like spin-orbit interaction, the size of the and shape of the trap, and everything, that it's practically impossible or requires a very fine tuning that you can nullify 3 independent functions with 3 dependent set of parameters varying 1 parameter. So therefore, in principle, you need 3 independent parameters to kill three independent functions. Unless of course, some of these parameters are 0 to begin with. And this happens, for example, if you demand symmetries. For example, time reversal symmetry. So essentially, how to explain it correctly? So essentially, there are symmetries that reduce the possible forms of this Hamiltonian, and for example, some symmetries make this Hamiltonian to be diagonal. And in this case, the number of independent coefficients is reduced, and then you need fewer parameters than in general. Okay, so symmetry changes the classification of spectrum degeneracy. Okay, so this was just a brief reminder of quantum mechanics degeneration, and then we go to relativistic spectrum, Dirac equation. So Dirac equation originally comes from relativistic physics. So everything was originally discovered there by people like Dirac and Weil and Majorana, who thought about relativistic quasi-particles, but we will borrow from them generously. Okay, so let's go back and remind ourselves what is Dirac equation. So it was an equation which is linear with respect to time and linear with respect to coordinate. So right now this equation, alpha is a 4x4 matrix, alpha and beta are 4x4 matrices. So psi is a spinor with four components. And so matrix alpha, so vector alpha and vector, so matrix alpha and matrix beta squares to 1, and different components of this matrix anti-compute, and matrix alpha anti-compute with matrix beta. So this what people demanded in general relativity to have this equation to be consistent with Lorentz invariance. Then, so this is what is called Dirac equation. Then it was claimed by Weil that one can. So yes, that was for relativistic equation. So the spectrum of this equation would be like this. So this is a relativistic spectrum of Dirac fermions. Then Weil showed that you can also take this equation for the limit of zero mass. So one can make this equation for massless fermions. Massless fermions. Mass equal to 0. And in this case, you can always choose beta to be tensor product of identity matrix and sigma x. So this is 2 by 2 identity matrix, and this is 2 by 2 sigma x. Beta square to be identity matrix tensor product with identity matrix, also 2 by 2, 2 by 2. And alpha is a set of matrices which is a product of the vector of Pauli matrices with tau z Pauli matrix. So vector of Pauli matrices is just sigma x, sigma y, sigma z, and these are conventional Pauli matrices. Tau z is the same as sigma z, but just in another part of our tensor space. Okay, so then you can notice then this object, which is a cross product of identity matrix with tau z, which did not appear so far. Is actually the same as I alpha 1 times alpha 2 times alpha 3. These are these guys. So you take alpha 1 is sigma x and so on. And then, and people, Dirac called this gamma phi Dirac matrix. So essentially you can now show that in odd dimension space, they're now in 3 dimensions, that in 3 dimensions that there is a matrix, this matrix gamma 5, this matrix gamma 5 actually commutes with all gamma 5 commutes with matrix alpha 1, alpha 2, and alpha 3, because gamma 5 is made of these matrices. So for example, if you compute gamma 5 with alpha 1, there are 2 matrices here. Matrix alpha 1 itself, with which alpha 1 commutes, and matrices alpha 2 and alpha 3, but alpha 1 and alpha 2, alpha 1 anti-commutes with alpha 1. Let me write it. So alpha 1, alpha 2 is equal to minus alpha 2, alpha 1. Alpha 1, alpha 3 is equal to minus alpha 3, alpha 1. So it anti-commutes with alpha 2, it anti-commutes with alpha 3, Therefore, it commutes with their product, and it also commutes with alpha 1. Therefore, this thing is just 0. And therefore we have a Hamiltonian, and we also have an operator that it's called gamma 5 that computes with the Hamiltonian, which means that we now can use this operator and label the states of our Hamiltonian not only as eigenstates of the Hamiltonian, but also in accordance to their values with respect to gamma 5. So it means that we now take this guy, which is gamma 5, and in this case it's one tensor product sig tau z. This operator has two eigenvalues, plus and minus 1. So it means that we have two spinors that can be labeled plus and minus 1 that will have eigenvalues plus and minus 1 for this operator gamma 5. And therefore our 4x4 Hilbert space is now reduced to a tensor product of 2x2 matrices. So there's 2x2 matrix here and 2x2 matrix there. And we can write an effective Hamiltonian for this subspace and for that subspace. So this will be plus part of the Hamiltonian, that will be a minus part of Hamiltonian. And this Hamiltonian, that will be relativistic Hamiltonian, and they will be equal to so these are 2x2 matrices. This is a vector of Pauli matrices multiplied by the vector of gradients. And I set some effective velocity, some speed of light or thermal velocity to 1. Okay, so that was invented. This Hamiltonian was invented by Weil in 30s last century. Okay. Right. So yeah, so this Hamiltonian was invented because it was proposed as an effective Hamiltonian for relativistic elementary particles. And now, of course, we don't have relativistic elementary particles, but we have materials that have a spectrum that mimics the spectrum of relativistic elementary particles, in particular Weil semimetals, and therefore we will just copy paste achievements of Weil and Dirac for our purposes. Okay, and see what is special about particles with relativistic spectrum if you study them in real materials as opposed to the vacuum of relativistic physics. So now we have a situation when some effectively two-band Hamiltonian that schematically looks like this. So we have something that has touching or near touching of conductance, conduction band, and valence band. And now we need to extend our treatment of quasi-particles that no longer can be assigned to a certain band, but now our reluctance are spinors that belongs to a combination of two bands. Okay, so right, so we go back. We go back to solid state physics, and we look at our what are they called? Bloch functions. Bloch functions, you probably know that, so I don't need to remind. Yeah, so it's so that is a standard Bloch functions, and then you construct object which is usually not mentioned in solid state one physics, you construct thing that is called Berry connection. Berry connection. So what you do, you have a Berry connection. It's a vector that depends on the position in K space. So this is a component of this vector, and it's equal to minus I. And then there is a scalar product of the Bloch function and A's components of the gradient in the K space acting on another Bloch function. So this is a vector. You take Bloch function, you operate with the gradient component A, you get a field that depends on the position in K space, and you call this field Berry connection. Now, if you take this field and integrate it along some closed loop, then the object that you get is called a Berry phase. So this is just a Berry phase that we all know from quantum mechanics 1. You can also take a curl of this gauge field. So it's probably wrong, but I consider this field just as a gauge field. And then if you take a curl of it, you get something that is similar counterpart of magnetic field. So anyway, so that probably are wrong words, but anyway, if you take a curl of it, you get this object, and its official name is Berry curvature. Okay, so now, so this Berry curvature, so it's essentially curl of Berry connection. Now you can take this Berry curvature. It's a function of K because everything here is a function of K. You can take this Berry curvature, so it's a curl, and you integrate this curl. Okay. So let's decide that we want to be in dimension equal to. Let us focus on two-dimensional systems. We will see soon why it's a good idea to focus on two-dimensional systems. So let's focus on two-dimensional system. Let's compute this integral over entire Brillouin zone. So this would be an integral over the Brillouin zone of f of k, and then the question what this object is. Now, normally when you have an integral of a curl, there is a theorem that says that it must vanish. However, that's because when people compute an integral of a curl, they assume that the manifold on which they compute is simply simple connected manifold. So if it's a simple connected manifold and it has trivial topology and no holes in it, then this thing is indeed zero. However, if you look at the Brillouin zone of two-dimensional system, it actually is a torus because these points are equivalent to these points, and these points are equivalent to these points. You can take more complicated shape of Brillouin zone, but of course it will be there will be always points on the boundary that you can identify. Therefore, from topological perspective, that thing is actually a something like this. It's actually a torus. And therefore, this manifold is not simply connected. in particular, if you take and look at it and try to imagine, and you make a loop like this loop is not constructible because it's encompasses this thing, yeah. As opposed to topologically, I forget the official name, manifolds like a sphere, where any loop is constructible. So probably that's a simple connected. Yes, the official name is simply connected manifold. So sphere would be a simply connected manifold, and all loops on the sphere will be constructible, as opposed to a torus where loops are not constructible, and therefore it's not a simply connected manifold, and therefore this integral is no longer vanishes, but you can show that this thing is actually quantized. It's integer. So this C belongs to integers. And this integral has a name. It's called Churn number. So this integer number has a name. It's called Churn number. Okay. And depending on your mathematical preference, you can play with it and show that that's correct. Now, Churn number has a well-known physical interpretation. We know that it emerges in the context of integer quantum Hall effect, because it's exactly the same object. Systems which are integer quantum Hall effect have the same topological index. It's called Churn number, and it has a physical consequences, namely Hall conductivity is equal to E square over H times this Churn number. So Hall conductivity is quantized in the units of universal conductance, and it's precisely equal to the Churn number. And it's something which is very well established for the integer quantum Hall effect. I'm not gonna cover this subject. There's something which is known. And manifestations of this thing, if you look at the spectrum of the, so if you have a sample, quantum Hall sample in the magnetic field, and you measure conductance, so what usually happens here that on the boundaries of the sample, you will have what is called chiral H star. So in the bulk of the sample is typically gapped. But if you look along the boundary of the sample, say, let's call this direction K parallel, then as a function of K parallel, the spectrum will look like some gap states in the conductance band, some field states in the valence band, and on top of it, we will have gapless states that will cross any value of chemical potential, and the number of these gapless modes that propagate along the boundary will be equal to the Churn number. So right now it's a filling fraction 3, Churn number 3, which is plotted on this figure. So this is a physical implications of a finite Churn number for quantum Hall system. And now what I just said, that if we happen to have a system with a very curvature, if it happens that we end up having a finite value of this integrated Berry curvature called Churn number, then the system is in the universality class of integer quantum Hall effect. Now, of course, what I'm saying is cheating. And you did not catch me. So I almost got away with my lies, and you didn't catch me. And so where did I lie? No, I didn't lie about torus. Or maybe I did, but I didn't know it. I don't admit. I lied about Weil semi-method. So if we will take a material like a Weil semi-metal, first of all, it will be three-dimensional material. But if we'll take a Weil semi-metal and integrate this three-dimensional material over the entire Brillouin zone, then what we would get would be a very trivial Churn number. It will be 0, right? For obvious reasons. Because roughly speaking, Weil semi-metal has an even number of Weil nodes, and it always happens that if there is a Weil node that has a Churn number +1, the second Weil node will come with an opposite Churn number, and therefore the total Churn number will be 0. However, if you would say, look at the three-dimensional Weil semi-metals and imagine that there are somewhere 2 Weil nodes, and it turns out that the minimal number of Weil nodes is 2. In practice, materials may have as many as 40. And I'll soon explain why the minimal number of Weil nodes is 2. But anyway, so let's visualize this picture. So the 2 Weil nodes coming in here. So this is the K space, and then they'll perform a cross section in the K space. So let's imagine that they take a cross section in the K space and cut K space along a plane. So we may have plane which is a blue plane. We may have a plane which is a purple plane, and we may have a plane which looks like a green plane. And now, if you play this computation of flux of the Berry curvature through these planes, so these are two-dimensional planes now, and everything that I said about computing Churn number for two-dimensional planes holds. So now we can compute a Berry flux, or Berry, what was its name? Berry Berry curvature, integrated Berry curvature through the blue plane, purple plane, and a green plane. Then I claim that for plane which is a purple plane, the Churn number will be 1. And for the blue plane, it will be 0. And for the green plane, it will be 0 again. That may be not obvious yet, and we'll show that later. But that would be the situation. So essentially, any plane which is placed in between Weil nodes will be equivalent to a quantum Hall state, two-dimensional quantum Hall state with a Churn number 1. And planes that are placed outside of the Weil nodes, they will be in the state which is quantum fold with the Churn number 0. So it's essentially quantum fold with no magnetic field. So what it would mean that states that are in between Weyl nodes must have gapless H states. So all these guys in the K space, they must that connect between these Weyl nodes, but in between these Weyl nodes must have a gapless H states, and these gapless H states are called Fermi arcs. So this cross section being in the equivalent class of quantum fold actually allow to claim that these states will have gapless H states, and they're called Fermi arcs, and they can be detected experimentally, for example, in ARCUS experiments. So in other words, there will be gapless surface states that are topologically protected. Whatever. Okay, so that's an observation. Now let us discuss why Weyl node comes in pairs, and this has to do with this combination of two symmetries. One is time reversal symmetry, and another inversion symmetry. Right. So time reversal symmetry for spinful electrons means that there is an operator, which we call time inversal symmetry, that squares to -1. In particular, if you look at the Hamiltonian, which is written in the K space and has some spin component, so if you apply time reversal operation to this thing, it will map all the state with the K to -K in all spins to the inverse. This is a time inversion symmetry acting on an effective Hamiltonian in K space. Now inversion symmetry, that's denoted by I. So what it does, it doesn't act on spin indices at all, as far as I understand. And it transforms K. It transforms K to state -2. So Hamiltonian, the state will be transformed by the time reversal to the Hamiltonian at the state -2. Now, what else do we know? We know that there is such a thing which is called Kramer's pairs. So what does it say? Correct me if I'm wrong, but I think it says that if there is a time reversal symmetry, that for each state K, for each microscopic state of Hamiltonian, say K and S, there is a partner state which is connected by time reversal symmetry, some partner state, let's call it K prime S prime, which obviously is actually -K -S. And this state, E of K sub S, and this state, this is time reversal partner, they have the same energy. So for each energy happens twice. So energy of a state Ks and the energy of its time reversal partner -K -S must be the same, provided there is a time reversal symmetry in the problem. That's a theorem by Kramer's. And these two states are called Kramer's partners. Okay, so now assume that there are two symmetries, this symmetry and inversion symmetry. Assume that there are time reversal symmetry and inversion symmetry. So what does it mean? It means that I can do two tricks. Let me start with state K and S and apply time reversal symmetry. So time reversal sends it to the state -K minus S, it has the same energy as the original state. Then I apply inversion symmetry. This guy sends me to the state K minus S. And because it's sent by symmetry, it has the same energy. So if I have both symmetries, I actually show that the state K S and K minus S have the same energy. So it means that the point K in the phase space is double degenerate. And that's correct for any point in the phase space. Therefore, all my bands must be at least double degenerate. So if I'm thinking about a spectrum that looks like a relativistic spectrum, then the entire upper band is double degenerate and the entire low band is double degenerate, which means that this point is water degenerate, 4 times degenerate. And this is actually what is officially called as Dirac spectrum. This thing implies 4 times degenerate at the Dirac point. Now, if we don't want to have full degeneracy for the touching point, but rather limit ourselves to the degeneracy 2, which is called wild spectrum, we need to kill one of these two symmetries, either time reversal or inversion symmetry. So we need to decide what we want to kill. So either time reversal or inversion must be, what is the nice name to kill? Removed. Must be lifted. The symmetry must be lifted. And sounds better. Okay, so or both. But we need so the conclusion from this hand waving argument that to have wild semi-metal, it must either violate inversion symmetry or time reversal symmetry, and this has of course implications for the choice of materials in where wild spectrum will happen. Okay, now suppose we have a material that has this structure, and this would be a 3-dimensional material. Okay, so let's think for a moment that we have a 3-dimensional material, and then in order to have wild spectrum, we need to have some crossing. So we need to have a special point in the K space, let's call it K0 as a function of K, where 2 bands cross. So if this thing happens, we can write a Hamiltonian, which is Hamiltonian that looks like this: K0 plus delta K times some identity matrix plus some set of parameters times a vector of Pauli matrices. And then if we say, okay, let's first of all ignore the term that comes with identity matrix. You don't have to ignore it, you can keep it. It would not change much. And expand this term in delta K near the K0 point. Now, if this point is not a special point, and it's generic point somewhere in the material, then we will end up having thing that looks like delta K times derivative of this vector of functions times times sigma. And if we'll call these guys velocity, then essentially we get a Hamiltonian that schematically looks like velocity times delta K times sigma. Well, I assume here that all velocities are the same. You may have a situation where velocities are not equivalent, but then it's equation of rescaling of k and changing the axis of rotation to make it diagonal, anticipating the equation. So it's some linear tensor of delta k, which you can always rescale and make to be a product of delta k with a set of Pauli matrices.
So when you expand around K0, right?
Right.
So you have scaled.
Okay, so let's do it.
Because I forgot to do vectors.
Yeah, so we have this guy. So alpha sigma. Okay, sum of alpha runs 1 to 3. Okay, so let's write dropping constant terms. We'll get delta k. Then delta k component beta d over dk beta f alpha at k0 sigma. Okay, and then sum with respect to alpha and beta. Okay, so now let's give it a name. So we will have something that looks like, let's call it this tensor. Let's call this tensor v alpha beta. So we'll have delta k beta v alpha beta sigma alpha sum of alpha and beta. So v alpha beta just a matrix of 2 by 2 matrix of constants. Right? So now let's assume that we can find a basis where this matrix is diagonal. It will be Vx, Vy, and Vz. And let's rescale all the k's such that they make all these velocities the same. Let's do a rescaling here at this point. So then all these Vx, Vy, and Vz will come and become some V times identity matrix. And then this Hamiltonian becomes V delta k sigma in the rescaled and rotated variables. But that would be an effective description of the vicinity of the Weyl node in a convenient basis. Okay. So then let us see what people would say. What materials? So to have this point, we need to have this type of crossing. And at the beginning of the lecture, I said that it's very difficult to have a crossing unless you have 3 independent parameters. Because you have 2-level systems and you need to have a crossing, so you need to have 3 independent parameters. So it means that if I look at my Hamiltonian, so my Hamiltonian, I have function of kx, ky, and kz. This is 3-dimensional material. So now if I explore my Brillouin zone, I actually do have, I can look at points inside the Brillouin zone of my 2 by 2 matrix as I vary parameters kx, ky, and kz. So from the point of view of counting, I do have 3 parameters. So it may or may not happen, but there is no argument that makes it unlikely that if I vary the parameters, I will find a point in the 3-dimensional Brillouin zone where these bands actually cross. And in fact, in some materials it does happen, and in some materials it doesn't happen. But there are many materials where it does happen. And And okay, one way to make it happen is to ask for additional symmetries. For example, to have materials where you have two orbitals that participate in the creation of the two touching bands. So imagine we have a material where we have s orbital and p orbital. Okay, that's as fine chemistry as I can go. And I don't know chemistry very much, but let's suppose that there are two orbitals. One is called s orbital, another is p orbital, and they're just two eigenvalues of angular momentum. Now, an s orbital is completely symmetric, so under the inversion, it has an eigenvalue +1, and p orbital is angular momentum, I guess, 1. Yeah, so it's anti-symmetric with respect to inversion. And therefore, if you have inversion symmetry, let's believe that for a second we have inversion symmetry and we have a band, then somewhere here, you will have a band of states that are built of p states, and we'll have band of static particles which is built of s states. So this is a conventional insulator. And now, if you manage by changing something, don't ask me what, invert those states, such that this will be to push up states that belong to s orbitals and lower states that belong to s orbitals, then necessarily we will get crossing points. And this is one of the proposals to make while seminar.
You kind of like hybridize S and P orbitals from different atoms.
Do they hybridize them?
So
Because when I hear words hybridize in the context of chemistry, I know what hybridize means for quantum in quantum mechanics.
So which system do you consider? So you have a lattice.
I have a lattice. I have atoms on this lattice built of two orbitals.
Meaning that like each atom is two levels.
Is two level system and has two electrons. One electron is and they have similar energy. So there are two states that have close energy. One is coming from s orbital, and another is coming from p orbital. And then there is a statement that if you are being able to do something which is, so if you think, if you've been able, without, so here we don't break inversion symmetry, to shift the band with s orbitals up and with p orbitals down by changing some parameter. So probably something that couples to p orbitals and doesn't couple to s orbitals. My guess would be magnetic field. But maybe I'm wrong. Maybe there's some other way to change, to couple differently to different orbitals. Then you will get points somewhere that depend on the degree of which you inverse the band. So if you change the degree at which you shift the bands, this point of crossing moves. So this point itself is somewhere in the Brillouin zone. Yeah? But just by the argument that you start here and end up there for this band, and you do exact opposite for another band, it means that somewhere these bands must cross. That the people who have developed intuition in chemistry say about chemical construction of these bands. So in practical terms, there is a bunch of materials such as this material, also simpler looking materials, that show characteristics of vial semi-metal. And if you know, you want to see the whole list with the details of spectrum and associated Fermi arcs, there's a very nice review paper by Bin-Guy Yan and Claudia Pelser, and I'll give you of condensed matter physics 8, page 337 to 17. So there is a list of spectrum, chemical structure, and beautiful realization of associated Fermi arcs. So what is important for us, for our purposes, that these materials exist in nature, that we understand that there are symmetries that we need to break, and these materials will have non-trivial Churn numbers associated with each vial node and associated Dirac curvature. So they will be different from the materials that we discussed so far, because we have not talked about aspects of degeneracy of the spectrum, and we did not talk about aspects of the Dirac curvature in the associated with this degeneracy. And now we will modify the conventional Boltzmann equation to allow our electrons to belong to the vial material type. So we're essentially interested in equations that we asked in normal metals. We can repeat these equations for semi-metals. What happens if we study transport in semi-metals where electrons are made of spinors that belongs to two touching bands, and when there is a Dirac curvature? And now some of the equations that we discussed so far will be unchanged. But for some aspects, in particular for Hall conductivity, there will be significant modification. And what we're going to study next time will focus on what is called anomalous Hall effect, and compute anomalous Hall conductivity for vial semi-metal. Now it's an interesting problem because I was working on it for the last 2 years, so I naturally think that it's interesting. But it's also interesting because if you look in the realistic materials, there are not many analytic results where you can take a material, compute it, and compare with experiment. And now if you look at any materials that on this list, they will typically have a large number of vial nodes. And they don't have experimenters don't have a theoretical prediction to which they can compare their measurements. So next time I'll show you a minimal model of a vial semi-metal, which we able to solve almost analytically, almost to the very end, and come up with a prediction, testable predictions. And for this model, the aspects of topology will be very important. So I think that's a logical and the last part of this lecture course, and it also shows that these problems of physical kinetics, it's not just last century physics, it's something that is relevant for their modern materials. So I guess that's the natural point to stop right now. Okay, so let's stop. See you